Hi, welcome back. Today we're going to be talking about sinusoidal function transformations. I realize technically we've already done transformations of trig functions, but today we're going to look at a few more examples of how to do it and how to think about it, I guess is really a better way of explaining it. I do want to point out the word sinusoidal because I'm not sure if it's come up yet or not. I'm trying to recall. It really applies to the sine and cos, basically the functions that kind of make the up and down shape, the wave that look like water waves. Tan is a periodic function, but it is not sinusoidal. Sinusoidal is just the bouncing up and down over and over again, like a water wave. Anyway, without further ado, let's move over to the lesson. Let's go through a few hints that we can use to try and figure out what the equation is going to be for a sinusoidal function that has certain criteria. First hint, the vertical shift will always be halfway between the maximum and minimum of the function. So for instance, if a function goes between 4 and 6, the midpoint 5 would be the vertical translation. It basically has an amplitude of 1 and has moved up 5. The amplitude itself is half the difference between the max and the min. Because the max is 1 amplitude above the rest position, the minimum is 1 amplitude below the rest position. So the distance between the two is 2 amplitudes. The period of a function, and the period I had mentioned before is a time, but in this case we're going to mostly be measuring it in angles, or our time will be the thing that we plug in like an angle. If we want to know what the period is going to be equal to 2 pi. 2 pi is the default period for a sinusoidal function. And if it's compressed by a factor of k, then it will be 2 pi divided by k. So for instance, if k is 5, we compress it by 5, so its period will be 2 pi divided by 5. And you can rearrange that to figure out what k you need. If you're given the period, k equals 2 pi over the period. So you can find your k from the period, and you can find your period from the k. All right. Vertical and horizontal flips. Ooh, that's horrible grammar. Vertical and horizontal flips are, can be. Yeah, that sounds like something I would write when I'm tired. Okay. Vertical and horizontal flips can be avoided by using phase changes. So basically, for instance, I could flip cos, or I could just move it over 180 degrees and make a crest into a trough. And we'll kind of see how that works as we go. Sometimes it's easier to do a flip, sometimes it's easier to do a phase change, and vice versa. So for question 1a, we have a function we want to transform. We have a basic f at x equals cos x function. We want to convert it into a g at x, which is an amplitude of 3, a period of pi, a phase shift of pi over 4 to the left, and a vertical translation of 2 units upwards. So I'm going to start by just writing out the generic formula for a transformed cos function. And it would be g at x equals a cos k at x minus x minus d plus c. So that's the most generic version we can possibly get of it. And now what we want to do is see if we can replace those letters one at a time. Amplitude of 3 means that our a value is going to be a 3. A period of pi. I could use our formulas that we just saw up here, these ones. But in general, if you can logic your way through it, I mean, just think about it. This one here, you can say k equals 2 pi over t. T is 2, so it's just k equals, t equals pi. So that's 2 pi over pi is 2. Or I can just look at it and say, wait a second, a normal sine function, normal cos function has a period of 2 pi. And I want to compress it to a period of 1 pi. Well, that's just half the width. So that should just be a value of 2. Compress it by a factor of 2. Okay, so we've dealt with a period of pi. Phase shift of pi over 4 to the left. That's going to be our d value. And a reminder, pi over 4 to the left means it's going to be a plus pi over 4. Technically, d is negative pi over 4, but in this it's x plus pi over 4 because it's x minus d. And finally, a vertical translation of 2 units upwards. That's our c value. So plus 2. Now what I'm going to do is graph g at x for 0 to 2 pi. And because I'm the teacher and I wanna, I'm going to completely cheat and not do it on paper because it's super time consuming and annoying. And I'm going to switch over to Desmos and do it there. So the first thing I need to do in Desmos is set up my graph grid so that it looks kind of like the one that I was going to graph it on. It's in radians. It has to go from 0 to 2 pi. So let's do that now. Go to settings. I'll turn this on to make everything a little bit more bold and easy to see. And then my x values have to go from 0 to 2 pi. So let's go to from negative. Here's a cool thing. If you punch in pi, pi, just the 2 letters, it'll convert it to the symbol pi. Let's go from negative pi over 4 to 2 plus pi, which would be 9 pi over 4. Now, the reason I always do that is because whenever you do, for instance, if you wanted to go from 0 to 2 pi and you make those the very sides of the graph, it usually screws up the axes because they're sitting right on the edge. So I usually go a little bit down and a little bit up. And my graph in the paper goes in intervals of pi over 2, so I'm going to go in intervals of pi over 2. I'm just going to turn that off for a second, and I think you can see that looks a lot like the graph paper that's on the paper sheet. Okay, I also want the graph to go up and down to at least positive 6 and negative 6. It already does that. I could modify my graph, but that's pretty good the way it is. I think I will, though, go up by steps of 1, just so that I can see the numbers. And, oh, there's way too many lines on there, so I'm going to turn off the minor grid lines. That's much better. Okay, so I'm going to graph the function. Actually, let's start by just graphing f of x, which is cos x, just as a reference. And then what I'm going to do is graph my modified g of x and see if it looks correct. So it should be 3 cos 2 x plus pi over 4. Oops, pi over 4 plus 2. So let's compare these now. So the blue one, I'm going to put a line on here just so it makes things a little easier to see. By no means is it required, but just the line y equals 2. And what that represents is the rest position of the blue graph. So basically the midpoint of the transformed graph. And you'll notice it's at y equals 2, which corresponds to the fact that, can I get you to see the whole thing there? There we go. That it corresponds to this plus 2 at the end. The whole graph's been shifted up 2. Okay, so has this thing had or does it have an amplitude of 3? Well, it goes from 2 up to 5 and 2 down to negative 1. It has an amplitude of 3. Does it have a period of pi? Well, it starts at 0. It goes down here. I'm just sort of to highlight those points. But it goes down and up again and starts repeating again pi later. So in 2 pi, it's gone through 2 complete cycles. So yeah, it does have a period of pi. Does it have a phase shift of pi over 4? Okay, phase shift of pi over 4. it's pi over 4 to the left. I hate to do this, but I'm going to just move over a little bit this way. Here's our peak. So if I move that peak pi over 4, yeah, it becomes that peak. So yep, we're doing okay there. And finally, does it have a vertical translation of 2? And I think that green line shows that it certainly does. So now that I've got that, I can say that g at x definitely does meet all the criteria and that we came up with the correct equation. Okay, that was a lot faster than doing this by hand. Let's try another one. We'll do this one a little bit faster and we'll do the erasing stuff. Okay, so we have f at x equals cos x, and we want h at x equals something cos something something plus or minus something. There's a lot of somethings there. All right, an amplitude of 2. That means there's a 2 in front. A period of 4. Okay, this is where your brain has to stop for a second and kind of comprehend what that means, because that's not a multiple of pi. So just to kind of get an idea in your head of what that is, you know that pi is 3.14, so this is going to be a little bit bigger than pi, which means that you want a period a little bit bigger than 1 pi being half of a normal cycle. So yeah, it's going to be around 2, but not quite. This is where, you know what, sometimes the formula is just more helpful. So up here, k equals 2 pi over period. The period is 4, so we'll just say 2 pi over 4. I'm just going to, over at the side here, say k equals 2 pi over 4. Just a reminder, 2 pi over 4 is pi over 2. Okay, so we have a horizontal compression of pi over 2, which is like 1.57 or something like that. We have a phase shift of 0.1 to the right. 0.1 is also not a nice number to work with. When it comes to radians, it's not a multiple of pi, but you know what? In this case, it doesn't matter. 0.1 to the right is just negative 0.1. The fact that it's not a multiple of pi changes nothing. And a vertical translation of 3 units down. Okay. Same idea. Let's switch over to Desmos and see if that looks kind of correct. Okay, so we have, I'm going to leave the base cos function there, and I'm going to modify this one. Get rid of that. Actually, I'll leave that there for a second. So h at x equals 2 cos pi over 2 x minus 0.1 plus, or sorry, minus 3. Is that right? Okay. To make this a little bit easier to verify that it's correct, I'm going to do something kind of weird. I'm going to go back into the settings and turn off the step of pi over 2, because that's multiples of pi. I want to point out this is not changing the graph at all. It's just changing the units in which the grid is marked. So it's completely legit. And I'm just going to change this to go up in steps of 1, just for the heck of it. So our regular cos repeated its cycle. Actually, sorry, let's do the amplitude first. That's the easiest one. I'm going to put in y equals negative 3, just so you can see the rest position of the modified function h at x. It does have an amplitude of 2. It goes 2 above and 2 below the rest position. So that's good. The period This thing had a period of 2 pi, which is, again, just a little over 6. We want a period of 4. Now, because it's been shifted over, I want to point out that this doesn't actually have a peak at 0. It has a peak at 0.1, but there'll be a peak at 4.1, so that definitely has a period of 4. A phase shift of 0.1 to the right. I think we just verified that. The peaks are 0.1 to the right of where they should be. And our vertical translation definitely does appear to be down 3 units, which is what that green line shows. So when all is said and done, I think we've come up with a perfectly valid transformation of our original function. All right, let's take a look at an actual word problem, an actual application of what we're learning. Amazing. So I don't know if any of you have seen these roundup rides. They come in different names, tilt-a-whirls, etc. But they're basically a big thing that spins on an angle. It's essentially a giant human salad spinner on its side that spins you around, and because it's spinning fast enough, you're pressed against the back and you don't go anywhere. So here's what we want to do. We want to model how high somebody is above the ground at various times when they're on this ride. So let's go with what we know, or what we're required to understand for our function, because when we're modeling, we need to understand what the function has to do, and usually picking a few points makes it easier to do. So first thing is we want to use a sine function, not a cosine function. We're going to be working in radians. It really doesn't matter since we're working with times. It does make sense not to work with degrees then. So on our grid axis down here, we are working with whole numbers. So we're considering these, 0 to 12 seconds, but we're actually going to think of that. Those are radian measures. Okay, and we need our rider to be at the lowest point at 0 seconds. The maximum height above the ground is 7.5 meters, and the minimum height is 1.5. And the wheel completes 1 turn in 5 seconds. Okay, so the lowest point is 1.5 above the ground, and it happens at 0 seconds. So I'm just going to draw a little dot there, and that has us at its lowest point at 0, and its highest point at 7.5 meters, and our time for 1 rotation is 5 seconds. Well, if it takes 5 seconds, after 5 seconds it's going to be back to where it started. 5 seconds later it'll be back where it started, and so on. By the way, I'm just drawing a graph to kind of get a start on it, because I find it much easier to find the equation if I can interpret what the picture's supposed to look like. I know that the maximum height is going to be 7.5 meters, and it's obviously going to be at the halfway point between being at its lowest points, because it takes the same amount of time to go up as it does to come down. So at 2.5 seconds, it should be at 7.5. And likewise, at 7.5 seconds, it should be there. So just that information alone, we've taken those things into account. We're going to have a graph that, to me, looks like this. Oops. Oh, this is going to erase way too much, isn't it? Haha. The downside of one fluid motion. Oh, stop. Oh, it erased way too much. Okay. Up, down, up, down. Okay, so it looks something like that. Just going to put a few notes on here. This is the max height. This is the min height. This is 1 period. So we have a fair bit of information there. Now that I have that graph, and I'm pretty sure that graph captures everything required in the problem, what can I fill in? Well, my height at time is going to be something, and we said it wanted to be a sine function, so let's do a sine function. something x something something. Okay, we don't have to do this, but the rest position is nice to look at. Since it goes from 1.5 to 7.5, that's a difference of 6. So halfway up would be 4.5. And that's the rest position. Okay, the rest position actually tells us exactly what our number for C is. It's 4.5. That one's pretty easy to find. Its amplitude, well, it's 6 from top to bottom, so its amplitude is going to be 3. It goes 3 above and 3 below. Our phase shift. Sine would normally be starting at the midway point at the rest position and heading up. So that means that this has moved over halfway between 0 and 2.5. So that's actually going to be 1.25 to the right. So this will be minus 1.25. And now the period. The period is always just going to be 2 pi. The k value is going to be 2 pi over the period. So it's 2 pi over 5. Okay, I think that's our formula. Going to take a quick second, a very quick second. Well, I guess all seconds are the same length, but I'm going to take a quick moment and go back to Desmos and let's see if this actually kind of works. So we want h at, I think it'll accept t as a variable. Some variables it's okay with, some it's not so much. I should probably relate that then. Oops, we're using a sine function. Sine t, h at t equals 3 sine 2 pi over 5 t minus 1.25 bracket plus 4.5. And just so that I can make this look a little bit more like the one we just did on paper, I'm going to just change these axes a little bit. I won't worry about the up and down, but I'm going to have this one go from -3 to, our graph goes up to a little over 12. Okay, so does that kind of look like, other than the fact that it's the wrong color? Starts down here at 1.5. At 2.5 seconds, it goes up to 7.5. Period's 5. Yep, that looks good. And the rest position looks like it's at 4.5. And it is. Okay, so perfectly good function. We know it, we've done it right. Next part is, can we find the same thing but using a cosine function instead of a sine function? Okay, well, I'm going to tell you the one thing that's kind of nice here, and that's that h at t, a whole bunch of things are going to be the same. It's going to have the same amplitude. It's going to have the same period. I'm going to leave a little space there, and it's still going to have the same vertical translation. So now we have two options when it comes to our picture. Which color haven't? Oh, I'm going to use a fancy color. Purple. Okay, I've got two options. If I want to treat this as a cos function, I can think of it as a cos function that normally would have its maximum starting at the x-axis, and think of it as being shifted over by 2.5. So I could give it a phase shift of 2.5. That's one thing I could do. Or I could recognize that since the bottom of it down here starts at the x-axis, that's really the same thing as just saying it's the negative cosine. It's the mirror image, or the vertical flip of the cosine. And that's actually an easier way to think about it. So I'm actually just going to say it's minus 3x at the front. And then I don't have to worry about a phase shift at all. Again, you can, and we'll do that when we actually go over and check it out. So again, let's verify that that one works as well. So I'm going to switch back to Desmos. I'm going to get rid of that. I'm actually going to just use this one up here. And let's see if it gives us the exact same thing. So I said -3 cos, and then pretty much the rest except for the phase shift is the same. I don't think you need a bracket around that, but I want it to be a t, not an x. Plus 4.5. And when I turn that on, yeah, I think those two functions are identically equal. They certainly look to be the same to me. I turn one off, you can see the other one. So those are good. I'm going to do just one more really quick here. And I mentioned that instead of doing, fitting, it's in purple as well. Instead of doing a negative sign there, I could just move it over 2.5 to the right. And again, those functions are all identical. So what you should be getting out of this is that there are multiple ways to express sinusoidal functions. Many of them can be equivalent. Some of them are just a little nicer. Now, I like this one up here, the red one, because it has no phase shift. I find phase shifts are the biggest pain in the butt to work with. It does have a flip, but I don't find flips that hard to deal with when I'm graphing. Sometimes you want a sine, sometimes you want a cos. There's not that's one better than the other. It usually depends on where the graph starts. If it starts at the rest position, sine's usually a good bet. If it starts at max or min, cos is usually a good bet. If it starts at a rest position and goes down instead of up, then use sine with a negative in front of it and it just flips everything. Oops. So yeah, that's all that negative sign does is flip it. Anyway, I'm going to go back to the lesson for just a moment, a very, very quick moment. Part C asks us to verify the models in Part A, which we did, or A and B, which we did. And I just want to make a little note about the homework here. So first of all, pay attention to units on graphs. You're going to have some graphs that have multiples of pi and some graphs that just have whole numbers. Sometimes it's easier to work in one, sometimes it's easier to work in another. Often with applications, it's easier to work with just numbers, not multiples of pi. But again, depends on the question and depends on your preferences. For question 17, there's a data set required for that question, and I have put that data set there. It's rather extensive. You can choose to use all of it or some of it to do the question. You can try doing it by hand, or you can do it in Desmos. You can enter points, and I'll show you really quickly. If you want to enter in any points, for instance 1, 2, you'll notice that black dot over there. Get rid of those, or better yet, let's make it more colorful. And if you have multiple points, you can do 5, 3, 7, 6. So if you ever want to graph points, and then once you've got those, you can always try to find an equation that matches them. Yeah, that equation's not going to work. How about 1.2? Sorry, I really like mathematical modeling. I find it fun to try and approximate. How about 1.1 plus 1? Not quite enough. 1.2. We're getting closer. Anyway, this is the idea of mathematical modeling. It's taking points of data and trying to come up with an equation that works. And the more equations you understand the shapes of, the more that you can try to match those patterns. Anyway, I'm going to leave it there. If you've got questions, let me know. Otherwise, I'll see you in the next lesson.